Okay, let's answer the second one first, right? That makes sense. So the entropy of the gas decreases, right? Well, this is an isothermal expansion, okay? In an isothermal expansion, the heat flows in. We have a positive Q. So that is out the window, right? Because we know that the change in S is change in Q over T. And if the Q is positive, then the entropy is increasing for that part, right? And we know that for this process, this is adiabatic, and the delta Q is 0. So therefore, the entropy can't decrease on that cycle, right? So it can't be that cycle, and it can't be this one, right? Let's look at this guy. Well, sure enough, right, we're taking this gas, and at the same pressure, we're reducing its volume, which, by the way, we know more about those particles. They're confined. It's a more orderly thing, right? They're confined in a smaller space. We have more info. Where are they? They're right there. They're in this tiny little space, right? But on this process, right, heat has to flow out. We have a negative Q, right? And so therefore it has to be BC because heat flows out, okay? So now we got to figure out the efficiency of this cycle. And what I do for efficiency is always the net work done divided by the heat in. Not the net amount of heat flow, but the heat that flows in. Okay, so the net work done, let's do that. So let's go AB, BC, CA. And what I like to do is just do this. Q is delta U plus work, okay? And they say the work done by the gas from A to B is 288, right? AB is isothermal, right? So therefore, the internal energy cannot change. So therefore, the heat that flows in is 288. Okay, that's the net amount of heat that flows in, right? Okay, and then BC, I think we figured out the work. No, we didn't figure that out. We know, though, that the thermal energy transferred, we know the work is negative 95 joules. There we go. Okay, so the work is negative 95. We know that this is negative 142.5. We know that this is negative, was it 238? Yeah. Right? And then for CA, we can do a little detective work here. We know that Q is 0 because it's adiabatic, right? Okay? We know that the net change in internal energy has to be 0. Okay? So therefore, we know that this has to be positive 142.5. And then we know that this has to be negative 142.5. Right? Because it has to add up to 0. So let's go through that argument again, right? If you add up all the changes in internal energy for a complete cycle, you have to end up back where you started. So therefore, this has to add to 0. Okay? Since we've got 0 in this has to be positive 142 for this to add to 0, right? Okay, therefore, we've got the work here. This is the positive work done. This is negative work here. So let's figure out the net amount of work. The net amount of work is 288 minus 95 minus 142.5. It's 50.5. Okay. The net amount of heat that flowed in is 288, right? So our efficiency is going to be the net work done, 50.5, divided by the heat that flowed in. Notice we don't do the net amount of heat that flowed in, okay, because that's not going to work, okay? By the way, this is 237.5, right? And if we add that up, if we go 288 minus 237.5, we end up with 50.5. So the net effect of this cycle is that 50.5 joules, a net amount of 50.5 joules flowed in and got turned into work. Along the way, though, we wasted a whole lot of energy, right? Okay. So 50.5 divided by 288 is the efficiency is 0.1753. What does it say? 172. See, I got like 0.172 or something earlier. I think that's using rounded numbers. But anyway, 0.175. Efficiency is 0.17 or 0.18. Okay, so when you do efficiency, just set this whole thing up like this. Okay, do a little detective work and figure out what all these things are, and then it's going to be the net amount of work divided by just the heat that flowed in. Okay, if there's more than one heat that flows in, you got to add them both up. This is heat flowing out, so I didn't count it. Okay.